Hey everyone, welcome to GEMCHEM. Now today's video is on aromatic compounds part 2 video, and already one video is uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And in this video, we are going to deal with the comparison between alkene and benzene and the salient features of electrophilic substitution when done on benzene ring. So first case, we are going to compare our benzene and alkene. So in this case, first we are going to see what type of reaction does alkene perform. So it performs generally electrophilic addition reaction, whereas in case of benzene, electrophilic substitution reaction takes place. So why this is so? Why it is different, though they have both double bonds? So in this case, if you see, the first step is that donation of electron to the electrophilic component of addendum. Okay, so here you can see there is an electron donor, which is our double bond. It is giving away its electron density to X, and Y minus is going out. As a result, this is being formed. This portion is plus in nature. Y minus combines with the carbocation. So here we can observe this one. So what we can conclude here is that the pi clouds not rigidly held, electron cloud very much easily polarizable, and initial reaction is fissile. Whereas if we consider in benzene, what happens is that there is also donation of electron to electrophilic component of addendum, but there is few more details which we need to know. You can see in this case of benzene, all the carbons are sp2 in nature, and this is a aromatic ring, right? So what is aromatic, antiaromatic, non-aromatic is already being discussed in the previous video. So you should first watch that and then come to this video for better clarity, right? So after that, when this double bond reacts with X, what happens is that there is a formation of sigma complex. This one is known as sigma complex. The other name for this one is also known as aromatic ion intermediate or wheland intermediate, that is WHELAND, that is wheland intermediate. So first one is ionic reaction, delocalized cation stable, right? Now what we will see is that here the resonance stabilization is being lost. One method can be you can take the Y minus and join it, and the second method is that just release this hydrogen and provide a double bond in this part, as a result of which it will gain its aromaticity. So for the first product, you can see that aromatic stability that we had in the starting material is totally lost in the addition product. Whereas in case of the second one, after deprotonation, the product is regaining the aromatic stability. This regaining is the driving force for the substitution. As a result, electrophilic addition reaction does not take place. And in this case, initial reaction, which is this sigma complex formation, is little bit difficult. Now we are going to see the graph for this one. So here you can see this is the reaction coordinate and it is the value of energy. So from here you can understand this delta G dagger of alkene and this is the delta G dagger for aromatic ring, right? So here we can see that this value is much more than that of alkene because the polarity of the alkene is very high. As a result, it needs very much less energy for electron donation. First step, what we have seen in case of benzene ring is that substrate becomes sigma complex. So first what happens is that there is loss of resonance energy, and second is that there is gain of energy due to the C and electrophilic bond formation. In the second step, we are seeing that sigma complex changes into product, that is there is gain of resonance energy and loss of energy due to the carbon hydrogen bond breaking. As the two-step process is energetically favorable, and if we sum up, there will always be a gain of energy. Now we are going to deal with our salient features of electrophilic substitution. So first case, what we are seeing is that in case of sigma complexes, these are generally unstable, but in some cases we can identify these complexes and characterize them at low temperature. One of the example is this one, where you have a benzene ring with CF3 as substituent. To add to it NO2F in presence of a Lewis acid, what you are going to see is there is a formation of sigma complex, And after that, when you warm it to room temperature, you are going to see a nitro compound being substituting the CF3 present in the benzene ring. So you are getting meta-nitrobenzene trifluoride. From here you can see that this sigma complex can be characterized and stable in minus 50 degrees Celsius, and this is crystalline in structure. Next is what? Its stability is associated with the stability of fluoroborate anion, which is this one, that is BF4 minus. Okay. Next example is our Friedel-Crafts alkylation. So in this case also, this sigma complex which we are observing is actually orange crystalline solid. It melts with decomposition at minus 15 degrees Celsius to yield our expected product, that is this one, and is essentially a quantitative yield. So we can see that this sigma complex is also being stable at low temperature, and here we are seeing Friedel-Crafts alkylation. As a result, alkyl group, which is ethyl here, is being added in the product. In the most cases, we can see the first step is actually slow and rate determining. Example, in nitration and bromination of benzene, we can consider the first step as slow and rate determining. There is loss of resonance energy, and in the second step it is rate determining for case of sulfonation. Third one is that most of the reactions are irreversible and are usually leading to the formation of kinetically controlled product. Two exceptions, which are sulfonation and Friedel-Crafts alkylation, there is a reversibility of reaction and we can see formation of thermodynamically controlled product. Now what do we mean by kinetically and thermodynamically controlled product? If you want to know about it, you can let me know in the comment box. I will make a separate video on that. The fourth one is that usually it shows a second order kinetics, that is first order with respect to the substrate which you are taking and the first order with respect to the electrophile which you are taking into consideration. And the last point which is essential is that it is subjected to the electrophilic catalysis. Not necessarily if aromatic substrate has high electron density, then it is requiring the electrophilic catalysis, but in most cases you are going to see Lewis acids as catalyst. But once you increase the electron density of the whole benzene ring, then you can ignore the Lewis acid. So let us see any two examples where reaction will occur without presence of Lewis acid. First is that when you are taking a phenol ring and as a result you are adding Br2 to it. Here what we can see is that this OH makes the aromatic ring more electrophilic. And in the next case you can see here aniline is being taken and you are adding bromine to it in presence of water. No Lewis acid is being required. You are getting a white precipitate of tribromoaniline. Here aniline is a effective electron donor. So these were the salient features of your electrophilic substitution. In the next video, we are going to deal with ipso substitution. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.